why is it the case that the improvements in computer vision have been, I don't want to call them incremental over the last few years, but they've definitely, we've hit a certain, I don't know if it's right to call it a plateau, but a point where things are already very solid. Whereas on the NLP side, it just seems like we keep pushing the envelope further and further. Obviously, GPT-2, which is still pretty recent, was a huge step up, but then quickly overshadowed itself as well. Like, why do you think there's such a difference between NLP and computer vision there?
It's a good question. And again, I'm not a specific like NLP person, but I think there's a couple of reasons. One of them is that, for example, the thing that really sparked the progress in computer vision was the ImageNet dataset, right? The fact that it was a huge corpus, a challenging problem that everybody could throw their algorithms at and sort of compare how well they were doing. And in the beginning, for natural language processing, there wasn't really like the go-to dataset to try your algorithm on, right? So in the last couple of years, we've seen a lot of new benchmarks that are now open source, available, and everybody can sort of compare their results versus others, right? In terms of something like classification accuracy, if you're doing classification, is a very clear metric. For natural language, it actually took a while before we got a good metric. We have a whole bunch of them. Something like the glue score, for example, is a good way to compare models. So we've seen a lot of progress on that side, kind of like making a uniform playing field that everybody could compare with. On the other hand, I do think that there was some architectural changes that we've seen. We've seen the transformer networks, right, where we're using attention mechanisms rather than the default LSTM-based sequence-to-sequence models. So there's definitely been like a big piece of the puzzle was made over there. And then I also think that if you look at these models, like say GPT-2 or something like BERT or T5, if you look at the compute resources that those things need, it does look like training those from scratch requires a significantly larger amount of computation than what we need to train something like a simple ResNet model, for example. So I do think that giving Moore's law like an extra year of time did also have an impact on that front.
Okay, so there, yeah, a lot of really compelling reasons there. The one that I think is maybe especially interesting to dive into, not that you're an NLP focused person, but still, you raised this question of essentially the loss function that we're trying to optimize for. In computer vision, we have categorical cross entropy or something like that because it's a straight classification problem. What is it about natural language processing problems that makes it so hard to come up with good performance metrics for some of these natural language models?
That's a good question and a tough question. I think the reason is that language is a system that's incredibly diverse, even starting from very simple principles, right? So if you were to define a language, like let's say a subset of English, and you would choose maybe 100 verbs and let's say 200 nouns, etc., even with a very simple subset of language, you would be able to create an enormous diversity of sentences that are actually meaningful. And I think that already hints at the problem, right? Language, for some mystical reason, has this capability of doing very complicated and very complex things with very concrete and simple building blocks. And so putting that into a framework of machine learning, for example, where the complexities are kind of tricky to sort of see how that is going to happen, starts with the problem, right? At the same time, language doesn't really have this classification kind of problem approach.
Yeah.
You can do something like text classification. Maybe a lot of chatbots today are using it, but really that's not exactly what we want, right? We don't want to classify sentences. We want to learn what they mean. And in that sense, another big problem, I think, in natural language, and this is something that I see the research community is now starting to try and tackle, is that for the past, I would say even 10 years, we've been doing NLP in the language domain only, meaning that all of these models, what they look at is ginormous corpora of text, right? So they only look at words, text, tokens. But I feel, and a lot of people would agree with me, that in order to truly understand what a sentence means, you have to have some kind of an embedded world model. You have to understand a little bit about physics, about agency, about, have to have language in combination with perceptual inputs, right? Whether you use a camera system or something about audio, I feel like these embedded language models, that feels like a very, very useful direction to explore.
Okay, so I might be at risk of going a little too philosophical with this question, but I'm going to explore it anyway. On the NLP side, one of the philosophers who I think is especially interesting to think about here is Jacques Derrida. And he brought forward this idea of words as being embedded in nothingness. Essentially, you could argue he kind of came up with the idea of word vectors in high dimensional space. So Derrida points out that like every word we can think of is really just defined by other words. So like if you were to ask me, Jeremy, what's an apple? I could only answer by referring to other words like tree or sweet or fruit and so on. So his argument is kind of that language is just this huge self-referential mesh, and that when you zoom out, you realize that it's actually suspended in nothing. It's just one word pointing to the next word and so on ad infinitum, but no one word is ever grounded in any kind of fundamental
Yeah.
reality. So in the same way, word vectors are all connected to each other.
Yes.
They're all related to each other, but that whole structure of language is grounded in nothing. It seems to me that what you're introducing with this idea of, we need this extra notion of physics, or we need some computer vision inputs to add context to this whole thing, is sort of like the step out of that, or trying to expand sort of beyond that and root our definitions in reality a little bit. Yeah, am I kind of getting that right? Or
yeah, I mean, I actually, I think it was almost 2 years ago, I actually started writing a blog post, but I never actually published it. That was loosely inspired by some famous philosophical experiments. But imagine the scenario that you have a newborn baby child, right? And you put this child in a completely dark room. It's a big black box. And the only thing that the child sees is a terminal where it can basically browse Wikipedia, but the text-only version of Wikipedia, right? So it can click links, it can read sentences, it can. So what this child, if it was really, really clever, and let's put all our ethical issues aside here, the child would probably figure out that there is a limited set of characters, right? And these are recurring. And then after a while, the child would figure out, hey, these characters, they actually have some patterns, right? There are words. And it might even figure out that those words, there is a certain ordering to them. And if you give it a sequence of some of these words, it might say, well, next to, following this sequence, I can give you a whole list of tokens that would possibly be put there, and a whole list of tokens that wouldn't be possible there.
Yeah.
So this is exactly what our language models of today are doing, right? They're looking for patterns in a huge amount of text data. But if at some point during that child's lifetime, you would put the sentence where it says, you are a child living in a black box and the real world is outside and you will never know it, I don't think that child would have a genuine understanding of its position versus that sentence. And I think that's really the crucial thing here.